All right, thank you very much. Thank you all for coming at 9 a.m. on a Saturday. I know that's really tough. At least it is for me. But hopefully you guys can learn something interesting about throughout the day. I think there's lots of great talks lined up. And also do check out DataKind because they are an amazing organization. Basically what I want to sort of get out of, first of all, I would like to get sort of a feel for the room because I think GANs, they're still a novel technology. It was basically, like the very first paper was published in 2014. And then ever since then, there's really been like a sort of Cambrian explosion in growth in this particular subfield. But there are certain prerequisites. It's not sort of a trivial technology. So I would ask you in a moment a couple of questions about your background so that I kind of know at what level to start. I will basically talk about some of the basics. We'll talk about some of the distributional stuff that's kind of required for you guys to start thinking about GANs in the right way. We're going to talk about the basic GAN architectures, and then we're going to zoom in on progressive GANs, which was kind of the most advertised paper because it's really flashy. It's now about a year old, but we can also talk about some of the more cutting-edge stuff. And then if there's time and interest, we can dive into some of the other fields. So first of all, how many here are familiar with deep learning and have trained a deep learning model themselves? Can I get a show of hands? OK, so about a half. How many would sort of know roughly what a GAN is and could describe it in very sort of simple terms? OK, all right, right. OK, so I'll probably spend a little bit more time just bringing people up to speed for deep learning, but yeah, then we can sort of have a look if we still have time for the other 3 points. Okay, so what is sort of supervised machine learning? This concept should hopefully be kind of clear to everyone, even if you come from econometrics or economics background. Ultimately, what you have is some sort of does this work? Yeah, perfect. So ultimately, you have some sort of data that comes in. You extract feature vectors. If you're doing deep learning, you probably have that done for you through the algorithm, as it sort of hierarchically progresses through the layers. And then you come in with these labels, right? And that's vitally important because then you combine those two, and then you have some sort of training process in which you learn what the mapping is between these feature vectors and these labels, right? And that creates your algorithm. So that's how you train, and then at inference time, when you put your model into production, you'd probably have a new document that you want to evaluate. You'd extract that same feature vector, or in deep learning's case, you just do that just run it through the neural network, and then you have this predictive model that came from this training process, and you get the predictive label. And that's how supervised machine learning works, right? That's pretty much, I'd say, like 80–90% of the deployed machine learning applications today. But of course, there's this whole other thing of unsupervised machine learning, which in many ways is much more interesting because you don't need those expensive, hard-to-obtain labels. You don't need to sort of worry about all sorts of things about model drift and things that change, as long as you can sort of start to just understand have the algorithm understand the nature of the data rather than having to figure out some mapping that can change over time, right? So the promise of there's lots of articles about the revolution will be unsupervised or whatever. How the next computing step will in machine learning will probably come for something that does not require these hard to get labels and actually starts to really bring us to models that have some degree of auto-inferred understanding of the world, right? Like they basically build out just from the raw data the understanding itself, right? So obviously the Richard Feynman quote. A lot of these fundamental mathematical lessons are pretty transferable, just because he's a physicist. I think it's still helpful for us to think about how hard is it to create something like the prototypical MNIST data set, right? So MNIST is one of those things that is really the hello world of computer vision, right? It's this 28 by 28, for those that don't know, grayscale image data set that just kind of is like what you do when you run your first convolutional neural network on just verify that it works, right? So here we're trying to actually generate them. So we're trying to understand what are the key properties that make a digit, and how can we go from something that looks like completely random noise in the beginning to something that actually looks like a digit that we can recognize, right? So obviously, a lot of the unsupervised machine learning has been heavily underappreciated because we struggled to make supervised machine learning at all work, right? Until about 2014, there was very little progress in deep learning in general, right? So we really need to sort of think about how this sort of fundamental building block that's now been to a large degree solved allows us to do this like sort of Cambrian explosion of further ML applications. And obviously, at the end of the day, what we're trying to do is trying to generate examples that look they came from the same distribution as our training set, right? So to some extent, for generative modeling, we're still trying to basically come up with a good representation of what the data is so that we can generate new samples that are not exact replicas of what we've seen in the training data, but are in fact, recognizable by us as humans. So ultimately, we need this generate function to be learnable, right? So we don't want it to be handcrafted because that puts us back to the age of symbolic AI, and no one wants to do that again, right? Unless you're Gary Marcus. But in principle, I think in that light, it's good to sort of highlight unsupervised machine learning from a sort of distributional perspective, because that's what you really need to start worrying about, right? Because you have, even if you have something like MNIST, which again is 28 by 28, so 768 dimensional vector, right? When you flatten it, then what that means is you need to come up with a representation for all those 768 pixel values that, as a whole, when reshaped, give you a meaningful image, right? For a mathematician, when you think about it as from a distributional perspective, that's a really hard problem, right? But it's not actually interesting from any sort of business or application point of view yet. But even MNIST, and I think if I remember correctly, this was, this is MNIST projection in TensorBoard. So when you just project the 768 dimensional space down to 3 using PCA, this is what you get, right? And then how would you even go about reasoning where a sensible example might live and where it's no longer sensible for that example to exist, right? So as a principle, it's really difficult to come up with a meaningful generate function on your own. So obviously, as generative modeling, you probably have some approaches that you've already seen, like the explicit modeling, where you try to have like something pixel RNN, where you feed in the subsequent pixels and try to generate a whole image of the data set. You can have variational autoencoders, Boltzmann machines, that sort of thing. You can also have implicit, where you basically don't try to represent any of that density, the probability density, explicitly. So you have some, like GANs are a part of this. Ultimately, all I wanted for you guys to take away from this slide is generating even a very simple example, such as MNIST, is really complicated. And the probability density function will not be trivial, right? So how do you generate a function that automatically learns how to actually come to that conclusion on its own without human intervention? So that's kind of where some of these problems arise, right? Because for example, you will have this probability density in the simple bimodal case, right? So you'll have some sort of true distribution, but the point estimate will probably be in the middle, and the maximum likelihood, naive maximum likelihood estimate will be sort of completely wrong, and it will actually have most of the probability mass when none of that should exist. But this is actually not an unreasonable representation of what an MNIST generated probability density function will look like. Because there will probably, because if you need to preserve the structure of the digit, there'll be very often cases where like a 9 will not, will have gaps in the middle, but some numbers, like 1, might have density there. So it'll be conditionally dependent on other things, and it will also have many different modes, right? That, like these peaks. So this is just a simple representation, but in principle, this will be in much higher dimensional case and much, much, much harder. So this is why it's hard. Now, let's talk a little bit about how we actually do it. So ultimately, what we want is to keep in some input vector, right? Some sort of random seed, so that we don't generate always the same digit. Ultimately, it's not interesting if all we achieve is some sort of MNIST generation that always produces the same digit. But what we want is some sort of control. So we have a sort of random vector, typically of 100 dimensions. I've seen people toy around with other dimensions, but it's not very successful for some weird reason. Then you take something like a decoder or some generate function that's machine learnable, and then in inference time, when you're actually trying to generate a new example, you just run this input, it does whatever it does, and then you get out the image. So on this simple like black box level, we just have random seed, run that through the learnable function, and get an output at the end. Now, what should this be, and how do we learn it? That's the hard question. So until recently, like about 2016, the state of the art was variational autoencoders. I will not go into them in too much depth, but basically it was just trying to come up with a representation that minimizes some reconstruction loss. But in 2014, GANs came along and really started to take off very quickly. So GANs kind of automate this process where this decoder function or this generate function actually becomes just a part of a more complex algorithm. So here we have the generator, which generates this example, discriminator, which evaluates the work of the generator, and then you have some sort of classification that comes from the discriminator. You also have some real data, so the discriminator has to tell apart which is a synthetic piece of data and what has actually come from the generator, and ultimately from this random noise through which it was seeded. So in other words, you're basically coming up with an algorithm that gets better because it sort of has to compete with this discriminator, and so it'll build up better and better representations of what ultimately what weights and values do I need to have, and that's how you actually arrive at those parameters that will ultimately drive a good realistic-looking examples. So, and then the discriminator just sort of classifies whether this is real or fake. So we'll go over this a couple more times because it's not the most intuitive of concepts. So in other words, basically you have generator that takes a vector of random numbers and then basically tries to create examples that are as realistic as possible. And then you want to generate fake data that are indistinguishable from the real data set. On the other hand, when you have the discriminator, what you're trying to do is either when you get an example from the real data set, which you don't know at that time, you're basically trying to label it as being real. And when you try to get an example that came from the generator, you're trying to say this is fake. And obviously, as you kind of go through this process, you kind of get better at telling which is which. So an analogy that some people use is basically like trying to come up with when you're trying to be a forger and you're trying to forge a painting of one of the great sort of masters, like some forgotten Da Vinci picture. You kind of come up with some picture and it's probably pretty terrible. And then you send it off to an art gallery in some random small town, and they have an art critic appraise it, and they say, look, this is not Da Vinci piece, this is definitely not realistic. So they sort of send it back, and you learn from that mistake. You like read up more. Maybe you even try to figure out what were the details that that made it possible for them to catch you. So you come up with a better painting. You send it off again, maybe to a different gallery, and then you actually you get accepted this time. But people then come and say, oh look, like this is definitely not a Da Vinci piece. This would have been in the Louvre or whatever. Like it's not meant to don't never be in such a small gallery. So then the art critic gets better, right? So the discriminator, the art critic, and the generator, the forger, both get better through this sort of competitive dynamic. So in other words, this is all sort of iterative process, right? So when you get this sort of real data that feeds into feeds through mini matches to the discriminator, and the second thing you do is you sample from some normal distribution typically. You feed it to the generator. You feed both of those intermittently to the discriminator for both the real data and the fake, and you get some classification errors, and iteratively train the discriminator as well as the generator, depending on where the error came from. Right? So you backpropagate the error through the standard like stochastic gradient descent that we all know and love. So does that kind of make sense so far? Yeah? Okay. All right, so obviously this wouldn't work with some loss functions. So what we're doing here is we're basically grabbing some, so this is the loss function for the discriminator, and we're basically, you're always trying to tell, you're trying to minimize the probability of the real example being misclassified as fake, and maximize the probability of the generated example being classified as real. And then in the original formulation in the 2014 paper, the generator's objective is literally just the negative of that. The nice thing about this formulation, even though it doesn't work super well in practice, is that one, it connects neatly to some statistical notions of KL divergence and Jensen-Chen's divergence when you look at what it's actually doing to the distributions. But more importantly, equally as importantly, it connects to this idea of game theory and sort of prisoner's dilemma. Because for those of you who are familiar, when you think about what these two players are doing, they're playing a non-cooperative game in the game theoretical sense. So there's a lot of literature that you can subsequently use that's already sort of solved this simple and much more complicated problems to start to reason about how does behavior to competitive players that are both trying to get better actually influence the outcomes. Now, in practice, as I said, people don't use this objective very often because it doesn't work super well due to some vanishing gradient problems. So instead of this sort of zigzag min-max training, I'll go into that. We have the non-saturating objective, which basically all it did is change this generator function to be still directionally against the, because you wouldn't have this 1 minus basically the predicted value of it being real off of the generated sample. So the GZ would all be like the generated example. So it's still directionally against each other, but it sort of solves the vanishing gradient problem. I won't go into that because that's a lot of technical detail why that happens. So why is this an interesting problem? Well, so generative modeling has been largely unsolved. Obviously, unsupervised modeling has a lot of really interesting potential. Typically, this was like the state of the art till about 2016 through variational autoencoders. You can see that they're very blurry. That has to do with the bimodality problem, because once you go into the outside of the space standard features, you very frequently would get a whole variety of backgrounds. Therefore, it can't decide and minimizes the error by just picking a value in the middle. So this is sort of been observed many, many times that actually generation through none of the other methods actually ever produces samples that look realistic and always produces this blur outside of the main facial features. And that's a really simple problem, right, to generate faces still, at least at this resolution. But there's definitely lots of applications. I won't go into that in a whole lot of details, but once you can generate more data, you can obviously, we always want, as data scientists, always want more data, so we can run some semi-supervised learning, data augmentation tools, and all of these have been tried in practice to just sort of help you get more data or do domain translation and all sorts of other interesting things. Well, why are GANs incredible? Well, because you saw this shitty picture from before. This is what is possible as of about a year ago. Now there's even better work from the same research group and NVIDIA. But really what you can see is 1024 by 1024 full HD images, full color, that all look very realistic. In fact, their latest work, StyleGAN, there's a website you can go to, which is thisisnotarealperson.com. And every time you go to that website, it generates you a new person that's real but doesn't actually exist. It's never sort of been that picture has been generated by the GAN from scratch. So none of these are real people, and yet we can consistently show all these faces that all have very recognizable properties, have sort of sharp facial features even outside of the main the main components of a face. So we've really sort of, in just 3 or 4 years, we've went from some uninteresting grayscale images, 28 by 28, to this. And there's a lot more to come. So I will not probably go into the manifold assumption. But obviously, this has been validated across many different data sets. So this is Elson, so it just images your bedroom. Can you sort of generate some other types of images? The one thing I would note, and I think you can kind of, the later, more mature GAN work shows this really a little bit better, but even you can kind of see it even here. Look at how it sort of learns the representation of the geometry, right? It learns that there's a meaningful sort of camera transitions that you can follow that will just not change the room, but like change some of the fundamental geometry, and sort of learns the 3D world without ever seeing the 3D world, because it only ever got 2D images. But it understands that the smooth smoothly sampling from this latent space, the random seed vector that we had in the beginning, remember? It just, when you sample around that area and have it generate more images, you get this smooth interpolation that allows you to basically have a degree of control of just the camera angle, which shows to us that it sort of learns how to represent the 3D nature of these objects fairly accurately, which is kind of amazing. Obviously, the other thing that's going on, apart from the geometry, is that every latent space, every vector in principle is meant to be a slightly different image. So obviously it changes the texture, changes the shape of the bed, and also all sorts of things, which currently there aren't that many ways to control which of the two you want to do, whether you want to do just translation or you want to actually fundamentally change the picture. So this is still an active area of research. Yeah, I will probably skip that. So in terms of popular architecture, so MessageTagging GAN is something that came in 2017 by Ariowski et al. Basically, it was just an improvement on the fundamental architecture. Basically, it very quickly, this architecture very quickly became sort of the academic and practitioner favorite. And the only thing that I would sort of say about this is that it allowed us to represent the probability density function that we talked about in the beginning, and of the generated data and of the real data, and sort of compare them. So now the loss function is more closely tied to how much error are we making relative to the probability density function of the real data, right? So it's just sort of, I mean, I don't think there's point in going too much of the mathematics right now. But basically, we're now, there's this sort of, now the discriminator is called a critic, and it's basically trying to evaluate the difference between the two distributions as a sort of singular number. What the work that we saw a couple of slides ago on the progressive GANs, right? So these full HD images, how do we get here? So what we needed to do is basically take this MessageTagging GAN and then really start to think about how do we navigate this like high-dimensional loss space? Like how do we navigate the, how do you force the generator to become better over time in this space where there's a lot of equilibria that are not actually very good images? So I'll just quickly go back to here. So when you see here, if you think about the probability mass that you actually want to look at, a lot of it is tied into these weird clusters in the space. So you can almost think of it as like archipelago or a set of islands, right? So there's the good probability mass, which are the islands, but they're sort of randomly distributed in this space. And there's a lot of space that produces like meaningless images, right? So when you see that all these samples right now, they're like horrible images. They don't actually, they have some like really distorted features or missing some features altogether. It's actually really these are really undesirable outcomes. What we want is all of our images to be in this land, but we don't know how this mass is distributed in this super high dimensional space. So we want to have a way of twisting this space so that it forces all the generation to only happen on land rather than on sea, where a lot of these undesirable outcomes happen. Make sense? All right. So this is what brings us here. So basically, we can think of the generator as a surfer, and the discriminator as some like Poseidon type figure who contorts the sea and sort of makes waves so that the generator's path to land is faster. So a way to think about it is every time you sort of have this generation, you start the generation or the training, you basically drop the surfer in a random spot in the sea, because that's the most likely position where this generator will start from. And then you get to the learning process. And through the learning process, you'll hopefully push that person closer and closer towards land, right? So obviously, there could be instances where this is too much of a complicated problem. So if we start with something that's the full HD generation, you get into this problem that you don't know which direction to go into, right? You're just dropped into the random point in the ocean, and then you're told to like get to the land. But you don't see the land. There's waves everywhere, right? The loss function is very complicated. So this is not a good place to start. So we want to basically push through the different loss terms to the surfer to the land through contorting that loss space, right? So how do we do that? Well, we start at a lower resolution. So if we sort of forget about this simple picture, we have a complicated loss space. That's only complicated because there's a lot of sort of local minima that we don't really know how to start to navigate this huge space. So we remove some of that resolution, and then we go to a situation where the space is much more navigable, and we start making good progress towards some of the good land and good equilibria, where the generator has actually learned how to create images that have some properties that we would recognize. So obviously, throughout the training process, we want to add this complexity back in. So in the paper, they start with a 4x4 image generation. You can see that that's not very interesting. But then we sort of increase the complexity, and we doubled the resolution. And as we do that, and we also gather the momentum to sort of push the surfer closer to land. So we get to one of those good outcomes. Right. There's a couple of things that need to happen in order for this to work. The one, I would just pick out one, but there's 4 fundamental improvements that this paper makes, which is the smooth interpolation, because I think it could help you guys with understanding. So obviously, we can't just double the resolution right off the bat, because that will shock the system. It will not sort of create a meaningful transition. And if all of a sudden you had a convolutional neural net and a transpost convolutional neural net on the other hand, sort of competing against each other, and then you just doubled the amount well, you actually more than doubled the number of parameters. If you then this would lead to a shock to the system, right? All of these are ultimately some parameterized models. You need to show it. Okay, this is still the same problem, but now we're sort of making it a little bit harder. So the way that you do that is that when you start with this 4x4, you just upscale it with some pre-existing sort of non-learnable models. So like bicubic interpolation, or things that Photoshop would already be using. Every time you zoom in too much into a picture, like that's what it's doing. It's doing something very naive when it's trying to basically like distribute out the average. There's no machine learning involved, right? But you also sort of start to train this higher doubled resolution layer on top of that. And then you have some sort of smooth parameter that slowly takes away the sort of non-learned representation and gives more and more weight to the learned representation. And you blend them together, right? So you slowly start to introduce this concept of another either generator layer or discriminator layer that creates this sort of higher dimensional picture. So that's how you sort of smoothly increase the complexity for both the generator and the discriminator. Yeah, I won't go into the code. So I think the other interesting area is sort of variation. Obviously, you don't want to get what is known as mode collapse, which is all of your examples end up looking kind of the same because the generator learns something that works, so it just keeps on repeating it, and it gets stuck in this local minima. And when the generator knows it works, the discriminator probably is already past the point where it can learn how to tell the two apart. So what they do instead is they basically spread out this data very early on in the process through some couple of clever tricks. I think I'd probably refer you to the paper if you're curious. So how do we know that this actually that any of this hard work that we have done so far actually matches up with the intuition I've presented so far? And how does the training process actually look like? So there's this helpful video. Ooh, if I can run it. Where we see the differences between the fixed resolution and the progressive resolution. Two great things that I would point out are, one, obviously, when you see that from the start, the progressive growing really starts heavily pixelated, but gets to outcomes that really look like human faces over time very quickly. The fixed resolution is rather unstable and sort of from the very beginning, even though you could argue that you get to something that vaguely resembles a human face much more quickly. But there's a couple of metrics on which academics judge their work, but the sort of fixed resolution tends to perform much, much worse on all of those metrics. But the interesting thing is that not only does it add you stability, but also it adds you quality over time. So it leads to a lot of desirable outcomes to sort of progressively introduce this complexity as you train, which I think is a pretty transferable idea to a lot of other machine learning models as well. All right, so in context, obviously there's the other three sort of big contributions that I mentioned, so equalized learning rate, pixel normalization, and sliced Wasserstein distance, but we won't get into that. There are sort of other architectures, including like spectral normalization and what's called a big GAN, which was actually kind of popularized by the media. I think there were a couple of like mainstream outlets, articles that even reported on it, that was created by Brock et al. At DeepMind. But overall, this is the growth. I don't even think this is an up-to-date picture anymore, but this is the growth of just GAN papers submitted to arXiv. Last time I checked, the original GAN paper had 2.5 times the amount of citations that TensorFlow has, which is kind of incredible when you think about it. It's really taken off very quickly. There's a lot of sort of research going on. There's still, the business thinking around this hasn't matured yet because it typically probably takes around 5 years to go from paper to production, and this has probably only been around for about 5 years. But there's a lot of like good work already sort of in this space. So there's pre-trained models on TensorFlow Hub. There are many, many extensions and many, many different applications. So most of them happen to be in sort of image generation, but it's by no means the restriction. This is a general purpose modeling framework that allows you to generate successfully music, sound, and voice, some tabular data. NLP, we're not quite there yet. There's some references if you want to take a picture. And I think I'll have time for a question or two. All right, thank you.
Thank you. Is anyone, we've got time for literally a couple of questions. Has anyone got one? Yeah? Sorry.
Thanks so much. Amazing talk. Thank you so much for that. I played a little bit with isthisarealhuman.com, the website to tell. And with a couple of friends, we realized that generated image have a couple of obvious properties. People tend to be more attractive, less surprised in some of the features, and they tend to look more at the camera. If you take the archipelago metaphor, I'm assuming that means that some of the real image are a bit more in the coves, in a harder to reach point from that exploration thing. Do you know if there's any kind of effort to generate images that are a bit less perfect?
Right. Yeah, great question. So I think there's a whole lot of work that's in this area, because obviously that's ultimately still had to do with this mode collapse problem, right? Basically, there's a couple of people that solve in really simple cases. It's very hard for the generator to move to areas where there's little density. If there's too much of a gap in the distribution, and there is no probability mass on the path towards some sort of weird but plausible equilibrium, or sort of equilibrium that's sufficiently far from the main probability mass, it will not make that jump usually. But at least that's the intuition we have some really simple cases. So that's one answer. The other answer is obviously it still is very heavily your data set dependent. So all of what you said is obviously true. Like also people have observed some of the images generally tend to generate females more often than males, and so on. There's a lot of, but that comes from the bias in the underlying training data set very frequently. So again, as always, you want to be careful about what your data is. Is it balanced on all the dimensions that you care about, right? All these things that are true in supervised learning are equally true here.
One more question, yes.
Yeah. Is there any sort of guarantee that if you took the set of all the possible inputs in your random vector, it would, for one or other of them, generate every possible correct output? Or are you only really ever going to get a tiny subset of all the possible realistic faces?
So there's obviously no guarantee that you'll get every single possible output, because it can only learn what it's seen to a degree. It will generalize beyond that, and it will learn things that it hasn't been told about, like the geometry and the 3D nature of the space. But it will not come up with things that were not at all represented in the training set. If it was represented at least a tiny bit, generally, if it's close enough to the original probability density, it will come up with a lot of meaningful interpolations between them.
Will every point within what you draw the diagram as land
yeah.
have non-zero probability of being the final result, given all the possible inputs in the random vector? Will it generate everything which is a valid solution given its training data?
I
Always have the vast majority of what you're calling the land, not actually everything else.
Right. Well, so I think it's almost a bit more philosophical question that you're asking, I think, because ultimately it's very difficult to tell what is, like, what are all the plausible, what do we mean by all the possible images of human faces, right? Like, do selfies count? There's a lot of other probability mass that it hasn't seen that will obviously not be represented. There's also training quirks. So inevitably, every now and again, there will be we will be able to generate an image which is not actually real, like it's not realistic in some aspect of the face or of the background or something. So there will be quirks as well. So there's both like the philosophical problem and the training problem, because this is still, machine learning is still an imperfect representation of the world.
Quite a big note to end on there. Thank you very much. If we could just thank Jakub for that excellent talk.